Welcome everyone. So this is our 51st live stream geometry, and we have 6 people here besides me. So today I'm planning on finishing up the Taiwan team selection test, or at least I think there still might be a few more problems left over after I do this session. And then we might move on to some other competitions. So with that, I will share my screen. Hold on just a second. All right, everyone see it? So this problem looked really interesting. It's like a very general problem. Let me maximize it. So we have a triangle ABC, and M is any point on the circumcircle. So let me draw the circumcircle. Then we have point M, and we draw the tangents to the incircle, and we see where they meet BC. So I think we're going to want to draw the whole line BC, and we're going to need the incircle. I feel like GeoGebra starts out slow and then it gets like faster. I don't know why. I don't know if it's like the computer reallocates the memory to GeoGebra or something. So I can close that now, and I will draw the tangents from M to the incircle, and I will see where they meet BC. Let me make it easier to see. So let me make it more like that. So they're calling it X1 and X2. So I'll just use what's in the question. And we want to show the circumcircle of M, X1, X2 passes through the tangency point of the A mixtilinear incircle. So I'll draw the mixtilinear incircle. There's actually, let me first make this look a little better. So does everyone on here know what the mixtilinear incircle is? I'll draw it in just a second.
Yeah, I know.
Okay. So let me draw the incenter. We'll call that I. And basically, all we have to do is, so there's a theorem. And so if we look at the midpoint of arc BAC, and we label it B, let's say, and then we draw DI, it meets the circle at the tangency point of the mixtilinear incircle. So basically, we want to show that M, X1, E, X2 is cyclic. Let's check that that's true. Yes. So that's what we want to prove. And I think, so if we actually want to draw the mixtilinear incircle, I think we could do this. So if you take the two midpoints of these arcs, so I did this in one of my videos, but and then you see where EF and EG cuts AB and AC, then the circumcircle of that, so HEJ, I think that's the mixtilinear incircle. Let me check. But I think I proved this in one of my previous videos. Yeah. So we don't need all that, so I can hide some stuff, but Just keep that. It's interesting. Seems like a very simple problem, right? But I've never seen it before. So we want to show that that's cyclic. How can we show something cyclic? We can use angles. We can use power of a point. We can use radical axes. Maybe even power ratio lemma. Or we can try to find another point that lies on that circle. I think that's sometimes the most common way to do it. So maybe there's some special point that lies on this, although I'm not so sure there is. The only thing I could think of is where AI would meet the circle, or maybe where ED would meet the circle. Let me just draw that point just to see. Is there anything special about point K? Oh, well, that has to be a coincidence. Yeah, KG is not tangent to the circle. No, it's not. Okay. Okay, I'm going to delete the circle. So let's see, what's a good strategy here? Yeah, it's really interesting that M can be any point on the circumcircle. Let me think about the power ratio lemma. I haven't used it in a long time. But yeah, I don't think that would work so well because we don't really have three circles. Well, we have two circles that pass through M and E, but we don't have a third circle. So otherwise it might work. Yeah, we don't have three different circles passing through M and E. Let's see. Could I join EX2? Yeah, I could draw those two segments, EX1 and EX2. Oh, maybe Poncelet's porism might maybe I could draw this point and this other point. It kind of feels like Poncelet's porism whenever we have two tangents like that. not sure how much that would help, but KL would be tangent to the end circle. All right. So I see Dat just joined. Thanks for joining, Dat. This almost looks isosceles. Wait, is this triangle? Yeah, by symmetry, it's isosceles. So it's like we have an isosceles triangle, and then by Poncelet's porism. Oh, is it necessarily isosceles? I don't think so. Because no, not necessarily. Okay. Yeah, I don't know if points K and L will be helpful, but is ME equal to MK? Hold on a sec, I'll check that. It looks like ME is longer than MK in that, in this. Yeah. And yeah, it's not isosceles, so. I don't really know if Poncelet's porism helps. I was just kind of an instinct because we have like two tangents like that. So we know angle x1 mx2 is angle LMK, which is 180 minus MKL. Yeah, I'm not sure again how helpful that is. Maybe it is worth, I don't know, drawing these points in. I'm not sure they'll be helpful, but we'll try it just for now. Okay, if we define E as the intersection of ABE and MX1, X2, so Hakan just had a suggestion. So I'm going to, okay, so we basically we define E as the intersection, or I could call it E prime as the intersection of those, or just E, because yeah, it doesn't say E prime in the question. Let's see. So Hakan is saying, hold on. And by Mikkel's theorem, we have KL intersects BC on the circumcircle of X1 LE. All right, so let me hide the Mixtilinear end circle. Let me hide this for now. So we want to show then so KL intersect BC. Whoops. So let me draw it. There we go. It lies on the circumcircle of x1 LE. So x1n LE would be cyclic by Michel's theorem. Interesting. And then also x2 n x2n ke would also be cyclic by the same argument. So we want to show D, I, and E are collinear. Could we do an angle chase somehow? Like, could we show angle LEI equals angle LED or something? I don't know. What if I drew EN? I don't think that does too much. Maybe, I don't think this is true. Maybe D is the midpoint of arc MO. KC is parallel to MX1. Ah, interesting. So KC is parallel to MX1 and LE is parallel to MK. I'm sorry, LB. Is that true? Actually, I'm not so sure about that. KC. Actually, now I'm not sure KC is parallel to MX1. No, like one's slanted. So they almost look parallel, but I don't think so. So like, no. Oh wait, is D really the midpoint of arc MO? It looks like it, yeah. So somehow, I don't know if I just got lucky. That looks like it's definitely true. Or at least it seems pretty true. Right? So basically, we want to reflect M across the perpendicular bisector of BC and let it be O. And then somehow EN and O are collinear. That's interesting. Is that really true? That just seems so random. Yeah, must be. Okay, so let's keep point O. We want to show EN and O are collinear. I don't know if that'll help, but And so MOBC is an isosceles trapezoid. So let's see, can we show by an angle chase? So angle ENB, we want to show that's equal to angle ONC, but ENB inverting with respect to I might work. Okay. And radius, the radius would be the radius of the end circle?
Yeah.
So that would take x1 to this point, x2. So if I drew these three tangency points to ABC, no, actually to mx1, x2, x1 would be the midpoint of, would go to the midpoint of these two tangency points. X2 would go to the midpoint here. M would go to the midpoint here. Yeah, I think that's not a bad idea. Just seeing where E would go to. So basically, whoops, wrong tangency point. Should be this one. So x1 would go to Q, x2 would go to R, M would go to S, right? So we have QRS, and let's see if I reflect, so I could draw those segments then. If I reflect E over that circle, and I get E prime, and I want to show QRS E prime is cyclic. So H is always going to be the same point no matter where M is. So if H is always the same point, that's what we want to show. We want to show that cyclic. But basically that's a 9-point circle. So we want to show E prime lies on the 9-point circle of HPJ. Seems like a good idea.
Can you name the other tangency points too, with AB and AC?
Okay, yeah. Just a second. Let's see. So T and U.
E goes to intersection of the altitude from H to TU and the 9-point circle of TU at H.
Okay, hold on a sec. So where did E prime go? Oh, I think I accidentally erased E prime, right? Sorry. So you said E goes to the intersection of the altitude with the 9-point circle?
A 9-point circle of TUH.
Okay, so the altitude from H, or
Yeah.
not that altitude? Oh, PUH. I'm sorry. TUH. Sorry. Okay, so. So wait, what was S? S is just the midpoint. Wait, is that obvious that that would happen? PJ and TU have the same midpoint?
That is actually not true.
It's not true. But the midpoint of PJ, is it collinear with T and U? Oh, I don't think. GeoGebra.
It isn't true. They're not collinear.
Okay, it's not true. So if we drop the perpendicular from H to TU, then E prime lies on it. Okay. How did you know? How did you know that?
I don't know the proof.
Okay. Yeah, because you can see there S doesn't lie on it. But yeah, that's so weird that E, N, and O are collinear. It's just random. So angle ENX1 is 180 minus X1 LE, which is angle MOE. Oh wait, I think it's trivial that E, N, and O are collinear, because yeah, angle X1NE is 180 minus MLE, which is MOE. So yeah, those are collinear, E, N, and O. And then we want to show EI and D are collinear. Invert again with respect to I. Okay, so so E goes to E prime, right? So when you said invert again, so how do you do that?
Can you draw the Sharky level point?
Oh yeah. I'm getting confused. So yeah, it looks like M is too close to it. So I'm gonna move M a little bit. So there it is, point V.
And you also name the midpoint of arc BC, not containing A.
Yeah. Whoops, sorry. Let me just draw AI.
It is enough to prove that VIHE is cyclic.
AIHE. Okay.
VIHE.
Oh, BIHE. VIHE. Sorry. All right.
It's true if you intersect BV, HN, and WE.
Okay. It's true. Sorry, DV. Thanks for typing it out. So WE. Okay, so let me draw those lines. Okay. So
I wrote something wrong.
oh, sorry.
It will be VA.
Oh,
not
okay.
VE.
VA. All right. Oops. All right, so those three concur. And I think I've done this. I think I did. Well, I don't know for sure, but it looks familiar. Is that like the radical axis theorem, or
I guess it was true from projective geometry.
Projective geometry. Okay.
And this proves the cyclicity and collinearity.
Okay.
It follows from Apollonius circle.
Apollonius circle. All right.
I think so.
Interesting.
Sorry,
Okay.
Michael.
Yes.
We can use, maybe I think we can use the lemma of so let AM intersect BC at a point.
AM.
Yes.
Okay.
And we will have let the parallel line from A to BC intersect this circumscribe ABC again.
Okay.
And let B1E intersect BC at a point.
Oh, B1H and E are collinear, I think, right?
Yes. So AHE A1 will consecutive.
Okay. AHEA1. Are you sure?
Sorry, M not A.
Oh, not A. Sorry. Did you say DHEA1?
M A1 H E. Yes.
Okay. Did you see a solution using that, or that's just something you noticed?
Yeah, I now right now I'm calculating some ratio.
Okay. All right, so I'm going to start writing up the solution that Serdar had, and then if you can figure out the calculation, then I'll do your solution too. Okay, so do we ever use K and L in these solutions? I don't think so, right? I think we can delete those. Is that true? Can I delete K and L? Right. Whoops. Didn't want to do that. Just hide a bunch of stuff. Okay. Okay, let me hide this. All right, I'm just trying to find the best way. It's hard to make the whole thing fit on the picture, but I will try my best here. Okay, so we're not going to see x2 basically when I write up the proof. So sorry. So okay, M. All right, so first I'm going to do Serdar's solution. So invert with respect to I with radius R with equals the in radius. Okay. And actually, I'll say let phi be an inversion. There we go. So we want to show that, okay, and let E be the intersection of those two circles.
Well, I defined E as the mixtilinear point.
Oh, okay.
And my solution is not done yet.
Is not what?
Solution is not done. I didn't finish the proof.
Oh, okay. So we're still thinking through it. Sorry about that.
If we prove that SQ, E prime are cyclic, then we are done.
Okay. Sorry. SQR and E prime. Is that what you said?
Yeah.
Yeah. So Nguyen, if you can figure out the rest of your solution, yeah, feel free to let me know. Let's see who's on. So yeah, it's well known that E, H, and B1 are collinear if E is the mixtilinear point. Okay, so EHA1M is cyclic. So angle EHA1 is angle EMA1. And we want to ultimately show that that's equal to angle EB1A. So we want to show EMA1 is EB1A. That almost seems like it would be a well-known fact, or One second, guys, I'll be right back. All right, thanks for waiting. Sorry about that. Power ratio lemma. X1b times X1c over X1A1 times X1H. That seems promising. Yeah, because then we would have 3 different circles through M, E, through M and E. So yeah, we could try to use the power ratio lemma. So X1B times X1C. You want to make it look like a cross ratio. I like that idea. All right, I'll just spend a couple more minutes and then you guys want to move on to the next problem? Unless you guys want. I like trying to use the power ratio lemma, but So Serdar, you said if VIHE is cyclic, that would solve the problem. If we could prove that.
Oh, I proved that.
Oh, you already proved it.
And
Okay.
we found that E prime lies on the altitude. And
Oh.
by using this property, we will
Hmm.
try to prove that SQ E prime R is cyclic.
Okay, so we know that E prime lies on the altitude. Yeah, that's not HS. Yeah, I have to use the perpendicular tool. Interesting. Okay, so we know that. Yeah, so is there anything special about like where the altitude of a triangle meets the 9-point circle? Well, yeah, that's the midpoint. Like if we have just any triangle in general and we draw the altitude in the 9-point circle. Oops, sorry. Yeah, so basically that's the midpoint of the orthocenter. Yeah, that's the midpoint of the orthocenter in C1. So that's what we want to show E prime is.
Let a point be on BC, like any point on that line.
Okay, hold on, let me delete.
What did you say?
Oh, no, I was just leaving that. Sorry.
Any
well,
point.
okay.
And then intersect AC1 with the circumcircle of ABC.
Okay.
And then EH and that intersection point will be cyclic, concyclic.
EH. EHC1 and B1?
Yes, if you define E to be the touch point of mixtilinear in a circle.
Okay.
I don't know if that helps, but
it's just it's something that's true. Yeah, that's what we did when we had K and L, right? That was that same lemma. All right, I'm going to move on to the next problem, but we can come back to this later if we find out more. All right, so for this problem, so we have a triangle ABC with in circle omega, in center I. D is the point of tangency with BC, and we also draw the circumcircle. M is the midpoint of ID. I feel like I've seen a problem before. Oh, we did this problem before. I forgot. I know we did this before. Let's see if we could solve it again. I forget how we did it though. A prime is the antipode of A. And X prime is AM prime intersect the circle. Or just X. And we want to show the circumcircle of AXD is tangent to BC. Do any of you guys remember doing this problem before? It was a long time ago. I don't remember how to do it though. Maybe let AX intersect BC at a point and then try to use power of a point. I don't know if that helps. So we want to so EX times EA is EB times EC. And we want to show that's equal to EB squared.
Michael, if you let the in-circle touch AB and AC at 2 points,
One sec.
and
Okay.
Yeah, and you let FG cut BC.
All right.
So yes, at a point, yeah. So E would be the midpoint of HD.
E would be the midpoint of HD.
Yeah.
Interesting. Because of that property, because we want to show that EB times EC is ED squared, and that's the same as showing that E is the mid, well, so do we want to show E is the midpoint of HD, or we know that that's true? I guess we could just try to prove it.
And then E would be the center of Apollonius circle. Like that should pass through the Sharky Devil point.
Okay. So that circle.
And delete this circle because we don't know if E is the midpoint.
Okay. So yeah, projective geometry looks like it might be useful here.
EJ looks like it is tangent to a certain circle of ABC.
Okay. EJ.
If the problem is true, it must be tangent.
It is equivalent to problem. Oh, okay. J, I, and A prime are collinear. Oh yeah, it's true. Maybe that will.
EJ.
Yes. Feels like projective geometry might work. Just not sure how. So yeah. So what if we project HED infinity through A onto the circle? So does HA meet the circle at a special point? Not sure. Then we have AD. Yeah, I don't know how much that helps.
Marco, can you draw the intersection of AB and ID?
AB and ID. So this point. Whoops, sorry.
Wait, sorry. AE and ID.
Oh, sorry, AE. Okay. So is there anything special, like if we intersect A prime B with the circle? So we'd have JX this point. We then project through something else. Yeah, it feels like projective geometry has to work somehow.
Maybe we can use the polar and antipolar.
Okay.
We will know that we need to prove HI parallel to ME. Okay.
ME.
And let X A prime intersect BCX at a point.
Let A prime.
X A prime. X A prime.
Okay. Whoops. I'll just leave it there for now, even though it's blue. So if that's L.
Okay, so we have EM we have EM is perpendicular to KL. And so
EM is perpendicular to KL using orthocenters, right? Yeah.
yeah, and so we need to prove HI is perpendicular to KL.
And
And,
HI is perpendicular to AD, so
yes.
interesting.
So we need to prove AD parallel KL.
Okay. Interesting. We also know that AXDL is cyclic, so maybe that would help because, oh no, why did I think that? Wait, why isn't that true? Oh, sorry, no, that's not true. But KXDL is cyclic, right? So we want to show AD is parallel to KL. So maybe we could show angle ADB is KLB. Wait, so sorry, I should erase that circle, but so yeah, AD is parallel to KL, but we know that KXDL is cyclic. So angle KLB is equal to, or KLB is equal to DX.
Okay, I got that. I have got that.
Okay.
So we have EL over EK.
EL.
Is, yeah, let me type.
Okay.
EL over EK equal to ES over ED, and we have ED. We have ED power 2 is equal to ES EI.
Okay.
And so we will have got the ratio.
Okay, so you're trying to show EL over EK is ED over EA, right?
Yes.
But we have so type it out in the chat. So EL over EK, I think you said it was let me see. sorry. So sorry. You have EL over EK is equal to, what was the first thing you said?
EL over EK is equal to EX over ED.
EX over ED. Okay. Oh, wait, that's okay. Okay, yeah, by part of a point. Sorry, I got confused for a second. And then EX over ED is ED over EA.
Sorry, maybe I have got some some problem. How did you denote E? E is the midpoint of HD or?
No, I define E to be the intersection of AX with BC.
Oh, I got that.
So I think it works, right?
No, because ES over ED equal to ED over EA is which what imply E is midpoint of HD, so we can use right now.
Okay. Yeah, because we can't do this last step because we're just assuming the circle's tangent when we do that, right? Yeah. Okay, so we want to show E as a midpoint of HD. I think that's a good strategy. Just have to find the right thing to project through, I think. Or we want to show AD is parallel to KL. Oh, sorry. Or we can try to show LI is perpendicular to HK. we want to show I is the orthocenter of HKL. So we could try to show that KD times ID is HD times DL, right? That would prove that I is the orthocenter of KHL. But I So M okay, so M is the orthocenter of KEL, right? So KD times MD is ED times DL. And then we want to show that I is the orthocenter of KHL. So it means that KD times ID is HD times DL. Hold on a sec, I think. Okay, let me write this out. So we have ED times DL. So we know ED times DL is KD times MD. Yes. And we want to show that HD times DL is KD times ID. And I think you guys might have already shown this. Why does it say playing music? I'm not playing music. So I think this might just go in circles because MD is half of ID. So yeah, we want to show that HT, E is the midpoint of HD. Yeah, it's just what you guys said. Okay. How should we do this? Project through. I kind of like projecting through A.
Point of ID,
Oh, what?
hard to see. Midpoint of ID goes to where? When projecting through A.
The midpoint of ID goes to F when projected through A.
No, we don't know where it goes, so it's the problem.
Okay. No, but I was thinking I like projecting H, E, and D through A. Onto the circle. So then we would get X. I'm not sure what this point would be. Oh, it's all right. So EXMD is cyclic. We haven't used that, right?
Intersect AD with the circle of AGF.
Okay.
Then that point of intersection should lie on that circle.
Okay.
I mean, I haven't proved it, but it looks like it.
It looks true.
Yeah.
Interesting.
Also, their H and I should be collinear.
All right.
And that I have proved, yes.
You can prove that, yeah, because they're both
Yeah,
right
that
angles.
is, yes, radical axis theorem.
Okay. So we want to show ED squared is EX times EA. Well, wait a sec, let's see something. I feel like we're really close here. So let's see. So do we know JNHD is cyclic?
Yes.
We just don't know that E is the center of it. So angle HJD, that's why, Hakan asked if we know that that's 90. Okay. Okay, so I could draw the circle. We just want to show E as the center of it, but we know the circle exists, right? looks like these meet too. Yeah.
Michael,
Mm-hmm.
if you let EM cut AD,
EM.
yeah, cut AD. Yes.
Sorry. At Q.
Yeah. And I define A as the midpoint of HD.
Okay. So the midpoint of HE.
HD.
HD.
Yeah. And I let A cut the circumcircle of ABC at point x prime. I will prove x prime is equal to x.
Okay. So
Okay,
so E prime is the midpoint of HD, and X
Yeah.
prime is the intersection of AE prime with the circle.
Yeah.
Okay.
So let's say E prime square, E prime D square is equal to EB times E prime B times E prime C, right?
Mm-hmm.
That will equal to E prime X prime times E prime A.
Okay.
But E prime D square is equal to E prime Q times E prime M.
Okay.
Yeah, so X A M Q is cyclic.
Okay. So X, or you mean X prime AMQ?
Yeah.
Okay.
So M X prime A will be 90 degree.
Okay.
So X prime M and A prime is collinear.
Okay.
And
All right.
yeah.
I think I got it. So I like that proof. So okay, I'll call this E prime, and this is X prime. Okay. Actually, I don't think E is in the problem, so we could probably just call it E. And we want to show. Okay, so I'm going to hide a bunch of stuff. I'm going to draw that back in just a second. I don't think we need N for this proof. All right. So now I'm going to draw in some more. Then we need to draw this. Wait, was Q the intersection of EM and AD? I forgot. Oh, EM. Sorry, I drew BM. That's why. Let me see. Anything else I need to do here? Oh, I'm just going to draw that point. It disappeared. Sorry. So yeah, I don't think we need L. I don't think we need this. Okay. So let FG meet BC at H. And then let E be the midpoint of HD. And let AD meet, let AE meet the circle at X prime. And then let EM meet AD at Q. But we want to show, okay, I'm going to hide this for now. We want to show that X prime, M, and A prime are collinear. So first, we have B, C, D, and H are in harmonic conjugation. So that means that ED squared is EB times EC. In fact, I'll do it the other way. So this is ED squared or well, no, actually we want it the other way, my bad. So that would be EX prime times EA. Okay. So what was the next step?
And then if ED square is equal to
EQ times EM.
times EM. Yeah. You okay, so you have to say that EM is parallel to HE and HE is perpendicular to AD. So
Okay.
EM is perpendicular to AD. Yeah.
So we have EQ times EM. So yeah, so we're using that AD and EM are perpendicular, and that's true because EM is parallel to IH, and IH is perpendicular to AD by poles and polars, I'm guessing. So basically, so EM is parallel to IH. So first, yeah. Also, since H lies on the polar of A, that means that HI is perpendicular to AD. And that implies EM is perpendicular to AD. So that's kind of how we get that, right? So then we have this. So that means AX prime QM is cyclic. I like your solutions are always very elegant. It's always like the nicest way to write it up. The cyclic. And so that means angle AXM equals 90, which means that for AX prime M equals angle AQM equals 90. So that means that X prime, M, and A prime are collinear. And that means that X prime equals X. And that means that the circumcircle, so I mean, basically that means ED squared is equal to EX times EA. And that means that the circumcircle AXD is tangent to BC. All right, that's our first solution of the day. Let's see if we can find another, but I really like it. It's pretty elegant. All right, so here's the next problem. It's a short one. So we have the in the circle of ABC.